Hi, I'm Carl Stamps. I'm a design engineer here at Technia.
Hi, I'm James Ford. I'm a simulation engineer here at Technia.
Hi, James. I've had some help from the rest of the team while I've been building my first finite element models, and I'd like to understand a little bit more about what I should be thinking about meshing the geometry. So I understand that a mesh is a way to break down the geometry into small cells, and that we can write an equation for the displacement for each of these, and that by solving all of the cells at once, we can calculate the behavior of the entire system. But are there any rules or best practices I should be following when creating the meshes?
Okay. Yes, so the basic concept, as you said, is to discretize or break down the geometry into a collection of connected but simpler shapes for which the displacement can then be calculated. With this information, we can then work out the stresses and the strains. Therefore, a suitable number of elements is needed to ensure both the geometric shape and the physical behavior of the material is actually accurately modeled. The exact number of cells doesn't have a hard and fast rule, but you need to make sure that it's suitably refined for the purpose of the mesh in that particular region of the geometry. Surfaces such as those consisting of curves require more cells than that of a flat cube. And for more complex shapes, a useful check might be to visualize the mesh without the element edges shown and to see if the surface is smooth or otherwise similar to that of the CAD geometry that the facets of the mesh are trying to conform to.
Okay, that makes sense. So it's purely a visual investigation then to see if the mesh contains enough elements.
So the visual investigation is one useful tool, but before you get to that point, you'll need to think about the objective of the analysis. This is in order to strategically use the right elements at the right mesh density throughout your model, allowing you to capture the behavior that you're interested in. It may be that you're only interested in the stresses at a particular feature of the model. And so here you might want to focus the quality of your mesh more than in other areas of the part. It may be that having run the analysis with this mesh density, that other regions of the part look like they need further attention, and therefore the meshing strategy might need to change and a second analysis is required. In these areas of interest, it's good practice to keep the element aspect ratio small and the shape of the elements regular. And you can then use mesh convergence studies to gauge how small the elements need to be in order to accurately capture the stresses in the regions of high stress gradient, and as importantly, whether the mesh is over refined and the computational cost of that analysis is actually higher than it needs to be. This can allow for the cost of simulations to be kept down whilst maintaining the accuracy of the results. To do this, the results of identical simulations, apart from the mesh refinement in the area of interest, are compared, and there will be a point at which the additional mesh refinement has minimal impact upon the results of the simulation, and an appropriate mesh density which balances the accuracy with speed of solution can then be chosen. This study can be done in stages with individual components or parts of components being refined individually.
That's interesting because I've had issues with mesh singularities in the past at sharp corners, and like no amount of refinement would resolve. How should I deal with this?
So you're right that no amount of refinement will solve this issue. And this is because the solution equations actually break down at these locations, hence the numerical singularity in the results. Therefore, it's best to exclude this region of singularity when refining the mesh and from the results, as otherwise you'll end up with an ultra-fine mesh in this region, driving the cost up without actually improving the results. This kind of goes back to what we touched upon earlier in the fact that increasing the mesh refinement can improve the results of the simulation. However, more elements equate to increased solution time. And as such, common practice is to actually refine areas of interest whilst maintaining reasonable refinement globally. You can achieve this by gradually increasing the mesh refinement as you approach the regions of interest. From a coarse mesh in a relatively unimportant region to an ultra-fine one, issues can arise within the solver or the results at the mesh refinement boundary, with the results being actually caused by the jump in refinement as opposed to a physical phenomenon. Conversely, an unrefined or a coarse mesh in a region that isn't of interest for accurate stress results may actually be appropriate, as here you may simply want to capture the stiffness of the part in order to drive the correct deformation in the area of interest. And a coarser mesh may be fine here, as the displacements at the nodes will be calculated with reasonable accuracy, even if the stresses in these elements derived from the displacement field is not due to the larger element sizes.
That's great. Okay. So I was wondering if you could also tell me whether, sorry, a bit more about the element types and the options, for example, the shape of them and the integration points. I see a lot of options in some of the software for choosing the elements to use.
Yeah, so there's several aspects that characterize an element, with the first being family, i.e. the shell, truss, or beam element, etc., that you'll have seen in these options. Different families have different applications, which can be found within the documentation. They also have different degrees of freedom associated with them. So you need to be aware of that when defining the models in terms of load, boundary conditions, and available outputs, etc. There are also options for the number of nodes per element, with linear elements having nodes on the vertices and the quadratic elements having nodes at the midpoint of the edge. This introduces additional degrees of freedom and allows for element edges to deform between the vertices, which means less elements may be needed. This comes with additional computational costs, though, and may not be suitable for all applications. So all of this needs to be considered at the early stage. There are also other considerations, such as the number of integration points within the element that the stresses are calculated, and that's something we can talk about in more detail if needed. It's worth spending some time understanding what the different element types are available to you in the simulation tool that you'll be using, so that you can design your model and the mesh based upon the most appropriate elements available to you.
Okay, thanks. So I've had issues sometimes meshing some of the more complex CAD parts. Are there any methods you'd recommend to achieve a better mesh without just throwing elements at them?
Ah, yes. So this is a common issue, and the one that there's multiple different ways to tackle. Perhaps the easiest approach is to, again, think about the area of interest in the part or the assembly that you want to simulate, and defeature the CAD geometry further away from those regions before you start building the finite element model. This will avoid the need for lots of elements to conform to radii and chamfers or even holes, etc., which will actually add no value to the final result. Remember, your finite element model at every level is an approximation of the real load, boundary conditions, and material responses, etc. This includes the geometry. So you want the best answer you can get for the minimum of input and computational cost. Once you are happy that your geometry is defeatured as much as it can be useful to simply split or part CAD geometry into more primitive shapes and volumes, which can then have a more regular mesh applied to than the complex geometry that it started off with. Say you were trying to mesh the geometry shown here, the filleted corners require a different level of refinement than the other corners, which can then lead to excess cells further away from this region of interest if the entire geometry is refined as before. An alternative to this is to partition the geometry, allowing for localized refinement to be carried out, minimizing the excess cells and reducing the resultant compute time.
Awesome, thanks for all that. I think I've got enough to be getting on with, and I'll check the documentation you mentioned for some extra info, or if I get really stuck, I'll give you a shout.
Perfect, no problem. Happy to help.